So let us continue with our discussion of the probabilistic aspects of coarse grained dynamics in a dynamical system. Just to recall to you what we are looking at, we have a certain phase space gamma, a region of phase space possibly into which the system is stuck, and then we partition that into cells of some given resolution. We look at a typical cell C, and the complement of it is C tilde, the rest of it. So we mark this cell, and then we are trying to ask for the statistics of recurrences to this cell. For this purpose we started with the following quantity. We said there exists an invariant measure for each cell. So mu of Cj, for each j there exists such an invariant measure. The total invariant measure is equal to 1. This is the a priori probability that if I just put a pencil dot on any given on the phase space, I would be in the cell Cj. Okay. Occasionally I will use the notation P of Cj for the same guy. Okay. The measure is a little more general because, as I said, there could be individual points in this cell which have a finite probability and so on. So we are allowing for that. Okay. Then the quantity that we want to compute is the probability that you are going to come back to this cell after a certain time n, and I call that R sub n for recurrence to this cell, and this was nothing but the conditional probability that you are going to be back at cell C in time n, and you are in the complement in the previous instance C tilde 1, given that you started in this cell at time 0. So that is the recurrence time distribution as a function of n running 1, 2, 3 etc. etc. Okay. So this is the quantity we want to compute, but because it is a conditional probability, we can also write this as P of C n C tilde n minus 1 all the way up to C tilde 1 and C0, and divide this whole thing by P of C, because the product of this times this conditional density is equal to this probability here. Okay. So we could always write it in this form. The question is, to compute this, what we did was to say, let us first define a probability Wn tilde to show that it belongs to the complement, which is the probability that you are in the complement at time n minus 1 all the way up to the complement at time 0. So let us just define this joint probability that you started in the complement at 0 and you remain in this complement of C till time n minus 1. Okay, so that is the definition of Wn, and it is immediately clear that W1 tilde equal to P of C tilde itself. It is the invariant measure of the complement here, because the whole thing is stationary, so the time index for a single time probability does not exist. We also defined for convenience W naught tilde is 1. We define it in that fashion simply so that the formulas look very uniform. Okay. Our target is this, but we could start by asking what is the probability of a sojourn in the complement for a given amount of time. So let us define sojourn probability H sub n tilde to be a sojourn in this complement. So it is the probability of C tilde at time n, C tilde at n minus 1 dot C tilde at time 1, given that you were in the complement at time 0. So all the normalizable probabilities will be those which are conditioned on something. So I say I start in the complement at t equal to 0, and what is the probability that I stay here till time n. Okay. That is the sojourn probability H sub n. Okay. H because halting, I halted in this complement here, okay. But this is equal to the joint probability with a C tilde 0 without the bar but a semicolon divided by this invariant measure P of C tilde. But this is obvious that from here that this is equal to Wn plus 1 tilde over the probability of C tilde, which is W1 tilde. Okay. And I emphasize that there is no question of normalizing this H sub n, they are all probabilities. There is no question of adding different n's because they are not mutually exclusive events. Okay. What we do know is that this set of numbers is actually a decreasing sequence. As n increases, the probability that you are going to stay out of C is going to decrease. Because it is ergodic, sooner or later the point will move into C. So as n tends to infinity, I expect Wn tilde to actually go to 0, okay. But we can show this quite rigorously without anything else, because I know that Wn tilde is a non-increasing, it is a decreasing sequence bounded from below by 0, because it is a probability, so it can't be negative. And there is a theorem in analysis called the Bolzano-Weierstrass theorem, which says that if you have a limit, if you have a sequence, a decreasing sequence which is bounded from below, then the limit exists, okay. I mean there is no reason why there should be a limit at all for Wn, it could oscillate or something like that, but the limit exists. So we are guaranteed limit n tends to infinity Wn tilde exists, and this is the so called Bolzano okay. It is a decreasing sequence, but the limit need not exist at all. But now we are guaranteed by this theorem that if it is a decreasing sequence bounded from below, then the limit exists, and it is bounded from below by 0 because it is a probability. Ergodicity then implies, and this is a crucial point, is actually 0. This probability has to go to 0 so that the probability of hitting C becomes non-zero, going into C becomes non-zero. So this is all the input we need, that this is a decreasing sequence and its limit point is 0 on this side, okay. So this gives us this the sojourn probability, and the next step is to ask what is the escape probability. So the probability escape probability out of C tilde, so let us put again over here E n tilde. This is the probability that you are out of C tilde at some time. So C n, given that you were inside at all earlier times, including C tilde 1, given that you were in C tilde at time 0. So you start, just for reference, let us keep this here. So this is C and the rest of it is C tilde. Yeah. So you start by saying I start out here, but at time n I am inside here, okay. I have escaped from this complement, having stayed there till time n minus 1, at time n I get in here, okay. So the question is what is this probability equal to? Well, again it is a joint probability divided by the invariant measure of this guy, so we can certainly write it in that form, but we can do it in yet another way, and it is related, and that is to consider h n tilde. What is this equal to? That is written down here, okay. So just for reference let me write it down just below that, P of C tilde n, and the rest of the arguments are all exactly the same. Now what happens if you sum these two probabilities, these two conditional probabilities? Well, you given that you are in C tilde at 0, and then you are asking for the probability that you are in C tilde till n minus 1, and what can happen in time n? Either it can go out and be in C, or it can stay in C tilde. So the sum of these two must necessarily be the probability that you have had a sojourn till time n minus 1. So it is immediately obvious that E n tilde plus H n tilde must be the probability P of C tilde n minus 1, C tilde 1, given that you are in C tilde 0. Because it is a sum over possible final states next time, and that is the probability of whatever has happened till then, till that point here. Okay. But this quantity here is equal to H n minus 1 tilde. Okay. So that gives us our first result, which says that this escape probability E n tilde is equal to H n minus 1 tilde minus H n tilde. So it is the first difference of the stay probability. This is like minus d over dt, it is real in the continuous case. Okay. And it is physically very clear, but all you have done is to conserve probability. But we have got a formula for this, and this therefore is equal to W H Hn was Wn plus 1, so Hn minus 1 is Wn tilde minus Wn minus n plus 1 tilde divided by W1 tilde. Okay. So that gives us our first result. It says if you compute these numbers Wn, and we define those Wn's here, if you compute this number, then you have actually computed the escape probability out here in this case. And now you can check that this fellow is normalized, because it can either escape at time 1 or at time 2 or at time 3, whatever time. So let us see what happens if you sum this En equal to, well, this is W1 minus W2 plus W2 minus W3 tilde, all tildes, etc., divided by W1 tilde is equal to 1, because all the terms cancel out except the first term. Okay. So this is indeed a normalized probability. So because that is the only thing that can happen. We have assumed ergodicity, so this immediately says that sooner or later things will escape, but you allow for escape at any instant of time 1 onwards, and you have to get 1 as the answer. So this is normalized as it stands. You could ask for the mean escape time, that is n times E sub n, and you have to sum over n and normalize it. So you can, that is a trivial thing to find out here, what this n times this thing is going to be. Okay. It may or may not be finite. So let us find out what is the mean escape time. Mean time, it is like asking what is the mean first passage time. We already had experience with this. We found that even on a straight line with diffusion, mean first passage time was infinite. Even though the probability of hitting that point, in this case exiting C tilde, is 1, you may still have an infinite mean. Well, let us see what that implies. Mean escape time which is equal to, well, we have a formula here, so it is equal to 1 over W1 tilde times 1 times, if I write this properly, E1 is W1 minus W2, so it is plus twice W2 minus twice W3 plus thrice W3 minus thrice W4, right, which is equal to W1 tildes everywhere, which is equal to summation n equal to 1 to infinity, because you can see that each time it is going to be one shot of complete cancellation. So it is Wn tilde 1 over W1 tilde. It is equal to this guy. What can we say about this? We know that Wn's all decrease. It is a decreasing sequence, and we know that limit n tends to infinity Wn is 0. That is a necessary condition for the series to converge. The nth term must go to 0, otherwise the series will never converge. But it has to converge, go fast enough for it to converge. It has to go faster than 1 over n to converge. But there is no such guarantee, that this series converges. All we know is that Wn tilde goes to 0 as n tends to infinity. So the sequence decreases, but if it goes like, for instance, 1 over n, then this is going to diverge logarithmically. As you know, the harmonic series is infinite. Okay. So we have no guarantee at all, and therefore the mean escape time might still be infinite. Okay. So I want you to carefully note this, because it is going to lead to a very interesting result. If you start in this place, by the way, the C tilde could have been any one cell, you would get similar results always. If you start here, you are guaranteed to escape into this at some time, but the mean time to do so may be infinite, but it may be finite, we do not care. But that does not tell us anything more unless you actually compute what Wn is and tell me what the large n behavior is. I can't say right away whether it converges or not. May or may not be infinite. Okay. Now let us look at recurrence and see what happens. So the lesson here is that the escape out of C tilde is the first difference of the sojourn in C tilde, okay, by this simple formula. This simple thing here. Now let us ask, what about the recurrence itself? And there I defined what the recurrence was. I defined it by saying the recurrence probability for the cell C R sub n is P of Cn given C tilde n minus 1 C tilde 1 C 0. Notice now it is C. So the statement is I start inside here at t equal to 0, and then I jump out and come back, and the question is, what is the probability of this happening in n time steps? Okay. So I start with that probability here conditioned on this, but I can also write this as P of Cn C tilde n minus 1 C tilde 1 semicolon C0 divided by P of C, the invariant measure of the cell itself. Okay. As always, I write this conditional probability as a joint probability divided by whatever is the probability of the conditioning. Okay. But this thing here, this here is equal to 1 minus P of C tilde, because the total probability measure is 1 for the full phase space, right. But that is equal to W naught tilde minus W1 tilde, because W naught tilde was defined to be 1 and W1 tilde was P of C tilde, right. So in this case the denominator is not W1 tilde but it is this, and this is a decreasing sequence, so this number is smaller than that, so it is positive, that is guaranteed. Now what can we say about this P on top? We need to write it out, and the idea is to write it out in terms of these W's, but W's refer to C tilde, so we have to be a little careful, and let us see how we can write this out explicitly. So we want this joint probability Cn C tilde n minus 1 dot dot C tilde 1 and C 0. This is equal to an integral over the phase space over the invariant measure d mu x. If you like, write this as rho of x dx, and x is the full over all the variables in the phase space, multidimensional integral formally, times that set of points where at time 0 you are inside the cell, and at time 1, 2, 3 up to n minus 1 you are outside, and at time n you are back in there. So the way to do this is to introduce theta functions, which when the argument is positive is 1 and when the argument is negative is 0. And in general when you have a multidimensional object like that, it is called a characteristic function, very bad name but that is the way it is, and it goes as follows. So we define the so called indicator function or characteristic function, but indicator function is better. It is just a big name called chi subscript c of x, and it is very simple. It is equal to 1 if x is an element of C, 0 if x is an element of C, the complement. So it is just a theta function, okay. But it is a very useful device, okay, because it helps us to do these integrals with constraints of this kind. Okay. Then what is this fellow equal to? This here you must integrate over all those points with this invariant measure which satisfy that. So you have a chi c of x that takes care of this portion, because this integral will automatically be 0 if x is outside. So the integral is now running over the full phase space, but this function sees to it that x must lie inside here, and then the remaining points. But remember that x evolves. So what is happening is that x k is given by, at time k, is given by some operator t, some time development operator t acting on x k minus 1. This is a time evolution operator. We do not care what it is. In a map it could be some very complicated nonlinear function. This is what I called f of x last time, but it is formally some time operator, and it is completely general. This whole thing is completely general. So even in a continuous time dynamical system you can take time slices, and what happens to any phase space point at time k depends on where it was at time k minus 1, and there is a map that carries you from k minus 1 to k. Okay. Let us call that map T, and this is iterated each time. The rule is not changing, it is an autonomous system. So this is equal to t squared x k minus 2 equal to etc. T to the n x 0, the initial starting point. So it is actually tracing the orbit. If you have a point here at some time, and the next instant it is there, next instant it is here, next instant it is here, and that is given by this map here, okay. So this time evolution maps the phase space onto itself, but it takes different points and maps them in different places, okay, and its iterates give you how the time evolution occurs. So we have ensured by this that the starting point is inside C, but in the first step it should be outside C. Therefore the next factor is 1 minus chi c of t on x. This is the indicator function of the complement of C. Okay. So if x is inside, if Tx is inside C, this is going to give you 0, because it is 1 minus 1 gives you 0. If Tx is outside C in C tilde, this will be 0 and you have got a 1. So you have got the full measure. and that should be true all the way up to n minus 1. So this whole thing becomes a product k equal to 1 to n minus 1 of 1 minus chi c of t k x. Okay. So just a compact way of writing something very complicated if you started writing it out in any arbitrary phase space, but this takes care of the fact that, so this is taken care of, this is taken care of, right up to here is taken care of. Okay. And then you got to be back inside here, so the next one has to be chi c of t n x. Okay. And that is the formal expression for this joint probability here. Okay. There is no conditioning. There is no conditioning on the initial state, on the initial point, except to say that it's, we want the probability that it's in 0, it's in C, not that given that it's in C, we want the probability, so we are integrating over it. But notice that by this device of putting in this time operator here, I have got rid of the need to introduce x1, x2, x3, these things as variables of integration and putting in delta functions all the time. I have buried all that by saying this map is iterated several times to give you this here. So if the first map x1 is some nonlinear function of x0, x2 is the nonlinear function of the nonlinear function of x0. So it can be extremely complicated, but we do not care. Notation wise this takes care of it completely. The next step is to say, alright, I want to relate this to the Wn's, so what we have to do is to replace this by 1 minus chi c of x and replace this by 1 minus chi c of t to the n x. If you did that, then you have added some terms and you have to subtract them out. One term you have already got, but you have to subtract out the remaining terms that you put in. I will leave the details to you, it's just a couple of lines of algebra. What happens is simple. If you took this here and this product, then it says time 0 you are in the complement, time 1 you are in the complement, time n minus 1 you are in the complement, time n also you are in the complement here. So it is not hard to see that this guy here becomes equal to W n plus 1 tilde, because from 0 to n you are in the complement, and that probability, joint probability, we call W n tilde. And then the term which involves just the chi and chi here on both these sides, that is also sitting there. And what would that mean? There's, when you multiply the 1 with the 1, 2 of these chi's are gone and you are left with 1 to n minus 1. But the integration variable is x, on the other hand the argument is t times x. So you are in a little bit of trouble till you realize that this is the invariant measure. So it immediately says, this is very, very crucial, invariant measure implies, remember what we said about the Frobenius-Perron equation. We said the density rho of x, the invariant density, does not change under one iteration at all. That was the whole reason why we called it the invariant density. So in formal terms this implies that d mu x equal to d mu of t x. So I change variables from x to y, where y is this nonlinear function of x, and the measure does not change, the probability measure does not change at all. So in the term which is 1, we change variables to tx, okay, and then it will look exactly like another w, and the w it will look like is 2 less than this 0 to n, which had n plus 1 of these points, but now you got n minus 1 of these points. So there is going to be a plus w n minus 1 tilde, and then in between you have two terms where you have this 1 times this with a minus sign and minus this times 1. again with a minus sign, and I use the same trick of changing variables to Tx in each case. And they will have the original thing had with the ones you had n minus 1 time arguments, with the full brackets you had n plus 1, and with one of them firing and the other not firing you have n of them, and the two are equal to each other by this invariance. Okay. You have to check this out, but I am just motivating it, it is very obvious here in this form. So you have a minus twice Wn tilde. Okay. But that is the second difference of the W's. Okay. So we are back here, we now can write down what this famous recurrence probability is. Rn therefore is Wn plus 1 tilde minus twice, let us write it the other way because this is a decreasing sequence, Wn minus 1 tilde minus twice Wn tilde plus Wn plus 1 tilde divided by now W naught tilde minus W1 tilde. That was mu of C, the invariant measure of the cell C. So we got a really interesting formula which says that the recurrence time distribution to the cell C is the second difference of sojourn probabilities in the complement of C. The first difference gave you the escape, the second difference gives you the return, but to C. Okay. Well, we can write this back in terms of I divide and multiply by mu of C, so this is equal to mu of C tilde divided by mu of C. This guy here is mu of C here, multiplied by Wn minus 1 and then a Wn plus 1. What was this fellow here? In terms of sojourn probabilities, Wn plus 1 was Hn. So this fellow is Hn minus 2 minus twice Hn minus 1 tilde plus Hn. So it is the second difference of the sojourn probabilities, and that is normalized. We have to check normalization, we still have to do this. Okay. So that is a closed form expression, this guy here, and the only assumption we made is ergodicity. We have just said this sequence Wn is a decreasing sequence, and that is it, with a limit point 0, and that immediately gives us this result for the actual distribution itself. You can, it is obviously the first difference of escape, that is also clear, because you can also show that this is like apart from something else, it is En minus 1 minus En times some constants, etc. Okay. Because we already showed that En is Hn minus 1 minus Hn, that is it. So it is just En minus 1 minus En. Okay. So that is an interesting physical way of looking at it. The escape out of the complement into the cell C occurs at time n with probability En tilde, and En minus 1 minus En gives you the recurrence probability, the second. That is a non-trivial result, it is not at all obvious to start with, but all we did was to use the invariance of the measure. The dimensionality did not matter, the kind of dynamics did not matter, how complicated it is did not matter, we did not assume it was chaotic, we did not assume anything, we just said it is ergodic in some region of phase space. So even if you have a dissipative system in which the system falls into what is called a strange attractor, this will apply on the strange attractor on that route. So all that you need is that the system is in some region of phase space and it stays there forever. We do not care what kind of motion it performs inside there, but it should be ergodic. Given enough time it should visit the neighborhood of all points in this part of phase space. Then this follows at once. We need still to check normalization, we still need to check normalization. So let us do that. Then we need to find the mean time. So the normalization would say that Rn tilde summation n equal to 1 to infinity, this is equal to 1 over the measure of C, that is W naught tilde minus W1 tilde times R1 is W naught, let me just leave out the tilde, minus 2 W1 plus W2 plus W1 minus 2 W2 plus W3 plus W2 minus 2 W3 plus W4 dot 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 here. So it is clear that the W2s cancel, the W3s cancel and so on, and you are left with W0 minus W1 which is in the denominator also is equal to 1. So this series telescopes everything cancels out except just the numerator and denominator, and it is normalized to 1. So this shows that recurrence is a certain event, sure event, okay. Again ergodicity. So if all parts of phase space are guaranteed to be visited given enough time by a representative point, then recurrence to any cell is a guaranteed event, probability is 1. So now we can ask what is the mean time to come back, and the mean time, mean recurrence time for recurrence to C, for return to any C, this is equal to 1 over W0 minus W1 tilde times 1 times this guy, so it is W0 minus 2 W1 plus W2 plus 2 times this guy, so it is 2 W1 minus 4 W2 plus 2 W3 plus 3 W2 minus 6 W3 plus 3 W4 and so on. So this cancels out, 3 plus 1 is 4, 2 plus 4 is 6 because this next term is 4 W4 and so on, W3 and so on. So everything cancels out except W0 on top. So this is equal to W0 tilde, W1 tilde, not tilde minus W1 tilde, but W0 tilde is 1, and this fellow is the invariant measure of the cell C. So we have a very elegant result. This is Poincaré's ergodic theorem, which says that the mean recurrence time to a cell is the reciprocal of the invariant measure of that cell. That is it, and that is exactly what we have got here. And that is the recurrence theorem, the ergodic recurrence. There is a corresponding theorem for Markov chains and so on. Well, we have already come across a trivial instance of it. You know, when you take a coin toss, that is not a dynamical system because all the tosses are independent of each other, but it is a Markov process because it is a Bernoulli process, and then if you have n coin tosses, this fellow had a geometric distribution for the first time you got a head or a tail or something like that. So if you say the tail and the head are 2 cells in phase space, and I ask what is the mean time it takes to get the head, to get into the head for the first time, it goes like 1 over p, the probability of a head, okay. That's, but the measure of this, the probability measure of the success is p, and 1 over p was the mean time. So that is actually an illustration of this theorem. It is this theorem at work in the case of a Markov process, a very, very simple Markov process. But here, even if it is completely correlated, we do not care what kind of dynamics it is, you are still guaranteed to get this result, okay. So it is a remarkable result, Poincaré's ergodic theorem. Now it has got consequences. It has got consequences for this problem of irreversibility in macroscopic physics. You may say, well, suppose you take an ideal case where you have classical dynamics operating and you have a statistical mechanical system, say the gas in this room, it has got a huge phase space, right, of the order of Avogadro's number in just the degrees of freedom, and now I ask, will it ever, it is a chaotic system, will it ever come back to any given cell in the initial, if you start with some initial conditions, will it come back to it or not? What is the recurrence time going to be like? What do you think will happen? This is the famous, there is many models of this, and the idea is the famous model is the checkerboard model. You have a checkerboard on which you start with some fleas, and the fleas are jumping from one square to another at random. Okay. So there is a discrete time, say every time step each flea jumps around somewhere here. So the question is, when will this system return to its initial configuration? It is an ergodic system, so it certainly will return, but the question is, what is the mean time it takes to do so? It is a finite system completely, the phase space is finite and so on. So the question is now, when is it going to happen? Will this happen at all? As you can see, if it is one flea and just one flea, then all you are asking is how long does it take for it to come back to its initial point on the average, one representative point. But now you are asking, when is the system going to come back to its initial state? That means every flea must come back to the initial point that it started from here. It is getting less and less probable, as you can see. It is not hard to see in this case that what will happen now is that the mean time will go like the exponential of the number of degrees of freedom. Okay, be enormous, because any given initial state has a very small measure compared to the rest of the states, because a huge number of states possible, and therefore this fellow will typically be of the order of e to the minus n. Okay. If you have two particles and each of them can be in two states, then the total number of accessible states is 4. If you have n particles, it is 2 to the n, so it is exponential in this, and the measure of any one of those states is 1 over 2 to the n. So if this is 1 over 2 to the n, this 2 to the n goes on top, and the mean time becomes exponentially large in the number of degrees of freedom. Okay. So even in an ideal world with no other things happening, the mean time of recurrence will go like the exponential of the number of degrees of freedom. Now even for the gas in this room, that will be of the order of e to the power n Avogadro. Okay. That is e to the 10 to the 23. Okay. It is so large a number that I do not bother to measure, I do not bother to specify the time units, right. Whether I call it picoseconds or femtoseconds or ages of the universe, it still does not matter. The age of the universe is only 10 to the 17 seconds, and a picosecond is 10 to the femtosecond is 10 to the minus 15. So this is a factor of 32 orders of magnitude, but we are here speaking of 10 to the 10 to the 23. Okay. So it is such a large number that the system appears irreversible. Okay. Of course many other things happen in between, so this explains why in large systems you do not, in daily life you do not see reversibility. It is highly improbable, and even if it is a sure event, it will not come exactly back to the same point, come arbitrarily close to the initial state, but it will take ages of the universe, or even far more than the ages of the universe to come back. So this kind of argument actually explains the reason for apparent irreversibility in observations. Okay. It is simply that when you have so many possibilities, the very specific thing that you want is not going to happen, and irreversibility happens. It can be said in many ways. For instance, when you park a car, it is much easier to get out than to get in, as you know, and you have all seen this. So assuming that people park normally in any normal country with human beings, there are exceptions, you have a spot like this, you have cars everywhere, you come along, and then what you do is to go forward and reverse into this, in this fashion. And you pull out in the same way, but it is much easier to pull out than to pull in, much easier. Okay. The reason is, you may say, why can't I just reverse my motion? Whatever I did to get out, I just reverse it in exactly the same way. The fact is that when you are getting out, when you get out and you are either like this or you are like this, etc., it does not matter, there is enough phase space. Many accessible, many possible microstates that you can get into, but when you are in here, there is only one microstate. You have to be like this. If you are in any other direction, you are going to hit somebody. Okay. So even though you have reversibility, theoretically you can just reverse the motion exactly, the aim has to be perfect while going in, but it does not have to be perfect while going out. So that is the reason for the ease in coming out, but the difficulty in going in, and that is an explanation of the fact that you have irreversibility in this problem, even though the dynamics is completely reversible. It again has to do with how many microstates are accessible, and that is one manifestation of it is this kind of theorem here. Now you might have one objection to this thing, which is to say, look, all this is nice in discrete time, but when I go to continuous time I am going to be in trouble, because if I put a time step tau, then this is tau over mu c. And now if I let the time step go to 0, this says the mean time of recurrence is 0. That is not true. In continuous time dynamics I still have recurrences, but this gives you a wrong answer, because it says you can't go to 0 sampling time. If you did that, you are in trouble. The reason this flaw was already noticed by Smoluchowski way back in 1916, and he proposed a modification to Poincaré which goes like this. The physical idea is the following: we included in recurrence R1. Okay. This corresponded to P of C1 C0 given. This is not a recurrence, you just stayed on. So there was no question of you going out and coming back, you did not do that, you just stayed on, and it is a fake recurrence. We counted this as a recurrence, and we needed it because I showed you that summation Rn is 1 provided you sum from 1 to infinity. If you sum from 0 up, or 2 upwards, then you do not get 1, right. So I very quickly buried that and summed it up in this thing here, but this is not a recurrence. It should not be included as a recurrence. So the way to do this is to say, alright, I have a tau up there, but in the denominator I must exclude this. So I must call Rn equal to the probability that I start at C 0, I get out at C tilde 1, and I stay out and get back at C n plus 1, C tilde n, etc. Now this is a true recurrence, because you told you start here, you get out at 1, and then you ask, I come back at time n plus 1, so the time difference is n again, and that is R sub n. Okay. If you do that, then you got to divide by this probability to find the joint probability, you go through similar manipulations. But what is this fellow going to be? This guy here says that you start inside the cell, you are outside the cell at time 1. So you put the characteristic function, etc., and work it out, and you discover this is W1 minus W2 and not W0 minus W1 in the denominator. And now you will sum over 1 to infinity and everything is going to be fine in this case. So this modification, because what happens is you have 1 over W2 in this case, in the limit in which tau goes to 0, this fellow will also vanish like tau, and so will the numerator, and there is a finite limit. Okay. And therefore you can go to a continuous thing here. So this modification was proposed by Smoluchowski, as I said, way back in 1916, and it has been looked at after that in several cases. Along with some collaborators, I have a paper on this which actually tells you how to handle this thing in the continuous time limit and to extend it to stochastic systems. We have not talked about that, I have not talked about it here at all. And then in the case of chaotic systems which have got phenomena like intermittency and so on, then very strange things start happening. There could be regions of phase space where you are stuck for a very long time and then you jump out, etc., etc. But now I want to pose the following paradox to you. We saw that it was possible that the mean escape time out of C tilde, so here is C, here is C tilde, and I said the mean time of escape out of C tilde could be infinite. But now I am saying the mean time to start here and to come back here is finite. That sounds weird, because to start here and come back here, I go out and then I escape from out back in here. Okay. So how come the mean recurrence time is guaranteed to be finite for ergodic systems by the Poincaré ergodic theorem, but the mean escape time to go from here to there could be infinite, depends on the convergence of this sequence Wn. What do you think is the resolution to this paradox? How do you think that is happening? You get the point, right? Because it looks like recurrence involves an escape out of C into C tilde and a return escape out of C tilde into C, and this mean time could be infinite, so could that be infinite. But we are saying this round trip is finite, mean time is finite. How is that happening? And the mathematics is quite clear, so there is no mistake in that. The resolution is that when you say average time, you are averaging over certain realizations of events. Okay? The recurrence time probability is normalized, so you are guaranteed that things come back, and therefore you are averaging over all those realizations of this random process for which the return is guaranteed. Okay? On the other hand, in the escape case, you are sampling over a different set of realizations. You are sampling over all realizations when an escape from here to there is guaranteed. That is it, nothing more. This is a bigger set, and therefore the average over it could well be infinite. So it is a question of what you are averaging over. Once I normalize a probability in that fashion, then I have said that I am averaging over all those realizations where the return is guaranteed. And then you have a finite answer for the return distribution. But this is over a different set of events here, just over the escape events. And it is possible there are some for which the Wn is so slow, decreases so slowly that it does not work. But another crude way of saying it, here is another crude way of saying it. If Wn is proportional to 1 over n, for instance, then sigma over Wn is going to be fine, infinite, right? Okay. Suppose it goes like 1 over n to n squared, what happens to sigma Wn? That is finite, right? If it goes like this, it is certainly not going to diverge in this case. But remember that when finding the recurrence time, you are taking the second difference. You are differentiating this guy twice more. So it is going like 1 over n cubed, and then things will be fine, etc. So each time you take a difference, you have a decreasing sequence, the first difference will go to 0 faster than the sequence itself, and the second difference will go to 0 even faster by a power of 1 each time. So it is entirely likely that you may have a finite recurrence time but an infinite escape time at all. This is entirely possible within this framework here. Okay. So there is a lot more that one can say here about this, but I thought I would give you a little flavor of what this looks like. One could ask, that takes us into a different subject itself, one could ask can we illustrate these general theorems using a simple model, a map or something like that. The answer is yes, but it again involves partitioning phase space. So here is a simple model which will do the trick. One dimensional phase space, so we have xn equal to some function of xn minus 1, some nonlinear function, and it is a one dimensional map of the unit interval, for example 0 to 1, 0 to 1, and the map is simplicity itself, but it is completely chaotic, and the rule is the following: start with any x0 between 0 and 1 and find x1 equal to twice x0 modulo 1. So this fellow says just double the number, and if it is less than 1 keep it, if it is greater than 1 throw away the integer. That is it, that is the rule. It is called the Bernoulli shift, this map here. And what does its graph look like? What does the graph of this guy look like? F of x equal to 2x modulo 1 says 2x would be a graph like this, slope 2. When x is 1 it is equal to 2, but you want modulo 1, so you cut that piece and put it back here, so it would look like this, and this is at a half. That is the map, okay? And this is the rule. Therefore if you start with x0, x1 is 2x0 mod 1, x2 is 2x1 mod 1, which is equal to 4 times x naught mod 1. And what does the iterated map look like? It has got slope 4 and mod 1, so it goes like this. And now the slope is 4, etc. No fixed points are stable in this case, and all fixed points are unstable, all periodic orbits are unstable, etc. And a typical point, if you start with an x naught, will, as time goes along under this rule, fill the entire unit interval densely and uniformly. You can show that the invariant measure is constant in this case, a typical point. But if you start with a rational point, it will be part of a periodic orbit. Any rational point will be part of, for instance, you start with 1/3, next time it becomes 2/3, next time it becomes 4/3, which is the same as 1/3, it's back to 1/3, 2/3, so it's a period 2. You start with 1/5, goes to 2/5, then it goes to 4/5, and then it goes to 8/5, which is the same as 3/5, and then it goes to 6/5, which is the same as 1/5, and you are back to a period 4 cycle, and so on. So any rational point will be a period cycle of some finite period, and those points will repeat themselves, etc. But the rationals form a set of measure 0 in the unit interval, and all irrational points are guaranteed to be part of non-periodic orbits. They are part of this chaotic orbit completely. Okay. So you can find the invariant density. You can now partition the cell, the unit interval, into say 10 parts, 15 parts, call each one of them a cell, and keep track of only where the point is, in which cell it is each time. And you can play this game. You can find Wn in this problem. You can actually compute what it is. So I suggest you do the following as the simplest case. Just do 2 cells. So C1 equal to 0 to half, C2 equal to half to 1. 1 is the same as 0 by this mod business. Okay. So call one of them C, call one of them C tilde, and find out what happens to Wn, etc. You can do this directly without too much difficulty. It is called the Bernoulli shift, because you know what is happening is that if I start with an x naught and it is a number between 0 and 1, so I can write it as 0 point A0, A1, A2, A3, etc. You can write it, irrational number will have an infinite decimal point expansion, which is not recurring, and I will do this in binary. So if you do this in binary, each AI is either 0 or a 1, that is it. And what does this A0 stand for? This number actually stands for A0 divided by 2 to the 1 plus A1 divided by 2 to the 2 plus dot dot dot. That is what this stands for in binary. So each AI equal to 0 or 1. If this is x0, x1 doubles it, and doubling it means multiplying by 2. So this becomes A0 divided by 2 to the 0. That means it comes out of the decimal point here. So at the next step implies x1 equal to A0 point A1, A2, A3 dot 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 dot. But if A0 is 0, then the number is less than half to start with, and when I doubled it, it was less than 1. But if A0 is 1, it means it exceeded 1, but I got to throw away the 1. So this is again 0. That is what makes the map non-linear. Otherwise it would have been just a linear map, but now I brought it, cut it down, it is non-linear. This means that if you give me an x1, there were 2 x0s from which you could have emerged this, got this x1. If you give me an x2, there were 4 x0s from which you could have got the initial point. So in the past there could have been 2 to the n points which are feeding into 1 point subsequently. Or another way of saying it is, in the forward direction, a difference of epsilon will become twice epsilon next time, 2 squared epsilon the next time, etc., till it becomes 2 to the n epsilon, where n increases without bound. And since you are modulo 1, it means that 2 points which are infinitesimally apart initially could become unit interval apart after given enough time. That is what chaos is. Okay. So this is called the Bernoulli shift, because you lose information about this A0. The next time you lose information about A1, etc. And that is what this multiple valued mapping is saying, telling you that you can't retrace the past uniquely. Okay. and it is called the shift because the decimal point is just shifted each time, one place to the right and whatever is on the left is thrown out. Okay. The map is fully chaotic, it displays, it is as random as a coin toss, it has a lot of fantastic properties here. But you can actually tell what is going to happen here. And now interestingly what will happen, you will discover, is that if you break it up into these two cells and keep track of only the cell it is in, call it left and right for example, less than half it is left, right, greater than half it is right. So you have a string sequence LR, LR, LR etc. Okay, just a sequence of letters here. Then it will turn out that the mapping to go from at any given time to go from one C1 C2 to the next C1 C2 becomes a Markov process. It's a two-state Markov process. So you can actually use the entire power of Markov processes to now talk about recurrences here once again. It does not always happen, this is called a Markov partition, but it is not necessarily true that it will always happen. It will happen if you break it up into 2 to the n pieces in this particular map. Okay. So let me stop here, and if there are questions we will take them up.